So I will fix a Calabi manifold of dimension 3 over C. So I just drop it like this. And the reason why I want to work with the Calabi, so Calabi means I fix a volume form, holomorphic volume form, trivializes the canonical bundle. So the reason why I want to work with Calabi, and the beginning of this story comes from string physics. And what string physics suggests, actually this is Witten, Candelas, Strominger, what they suggest is that if you want to, you want geometry to, like in general relativity, geometry of space-time dictates forces, it says gravity. If you want to do the same for other forces in the framework of string theory, you have to assume that space-time is locally of the form R4 with a Calabi. I don't know the reason for this, okay? It's not my expertise. So this is the beginning of the Calabi story in this context of Donaldson-Thomas invariance. And what they also understood, if you want to do Feynman diagrams, if you want to compute trajectories of particles, string particles in a Calabi, you will have to count curves on Y. The reason being, of course, if you have a string particle moving into space-time, as it moves in time, it will make a Riemann surface. There are reasons for this surface to be a Riemann surface. And what you want, if you want to count trajectories of particles in space-time, well, you have in particular to count curves in Y. And there are essentially 3 ways to do this counting. The first counting is, so curves, I mean algebraic curves. So the first way to do this counting is by looking at the moduli of all parametrized curves. So what I mean by parametrized curves, I mean the Kontsevich notion of stable maps. So there is a sense, there is a notion of a stable map, and these stable maps, essentially they are parametrized curves. They form a nice moduli space in the sense that the moduli space is quasi-smooth. Is actually quasi-smooth the Ling-Mumford stack. And the reason why we care about the quasi-smoothness is because every time we have a quasi-smooth the Ling-Mumford stack, you can define the virtual class, and you can actually define the volume of this moduli space. So the volume is well defined. And this is how people count these numbers. By looking at the volumes of these moduli spaces, of course, you have to fix a bunch of points, you have to fix the genus, and you have to fix the class of the curve in the homology of Y. A bunch of stuff to fix. This is the first approach. A second approach would be to count directly embedded curves. And of course, the naive way to do this would be just to look at the Hilbert scheme of codimension 2 in Y. The problem if you try this approach is that contrary to this one, this Hilbert scheme is not quasi-smooth as long as the curve is not quasi-smooth. So you have a problem here. Is that the volume is not well defined. Which brings us to the third approach, and this is the one I want to mention throughout the talk, is to say, okay, I can replace the curve by the ideal sheaf corresponding to the curve. And more precisely, instead of looking at the Hilbert scheme, I will look at the moduli space of coherent sheaves in Y. I'm being very imprecise here. I would have to tell you exactly what kind of coherent sheaves I want to look at. I want to look into. But in any case, this is the idea. And on certain kinds of coherent sheaves corresponding to ideal sheaves, actually we have a bijection on the coarse moduli spaces. The difference is that the deformation theory of a coherent sheaf is not the same as the deformation theory of the curve embedded. So has a different So what is this deformation theory? So the deformation theory, if I take a coherent sheaf in Y, the deformation theory is controlled by two groups. The first group is the group of infinitesimal deformations, and this is the group is the first X group of my coherent sheaf. And then there is another group, which is a group of abstractions, which is the second X group. And a nice feature of this moduli space in this particular Calabi case is that because of Serre duality, combined with the Calabi condition, these spaces are actually dual to each other. Okay? This one and this one will be dual. So I have an example of a moduli space whose deformation theory lives in 2 degrees, and there is a duality. So what this talk is really about is moduli space that have this nice feature. So So what I really want to tell you about is what kind of duality is going on behind what kind of duality is really going on here. So I will start by giving you a theorem without mentioning, there is a lot of buzzwords here, and then I'll try to explain what this means. So it's a theorem by Pantev, Toen, Rizzozzi, and Vaquier that tells you that this kind of deformation theory, quasi-smooth duality, are examples of symplectic forms. So this duality comes from a symplectic form on this moduli space. I'm lying if I don't, in order for this to be actually correct, I have to put a -1 here. And I have to tell you what a -1 symplectic form means. And I also, to be honest, I cannot just say that this is a moduli space. I have to consider a derived version of this moduli space, although it's not so relevant the moment you know what the deformation theory is. So what I really have, if you don't want to think about derived geometry, what you have is a moduli space with a specified deformation complex, and what you have is a symplectic form on this deformation complex. So the first thing I want to start by telling you about is what are these symplectic forms and how one should think about them. So this is part 1. Shifted symplectic forms. So before telling you what is a shifted symplectic form, maybe I should tell you what is a symplectic form. I'm sorry if I offend someone. So let's take X to be a smooth manifold. So a symplectic form is just a 2 form which is closed for the Ram differential, and such that it is non-degenerate, in the sense that if I look at the pairing, so a symplectic form gives me a pairing on a tangent bundle, and the fact that it's symplectic is, I need to ask that this pairing is non-degenerate, which means that the bilinear form, if I take a vector and I think of the form associated with this vector, this gives me an isomorphism between the tangent and the cotangent spaces. So the moment we have this, we can try to formulate a definition for what is a symplectic form in algebraic geometry. So, of course, if we have a smooth algebraic variety, we can play the same game. And we have even examples, easy. I can take the fine line, everything in this talk is over C. Okay? So this is the cotangent complex of the cotangent bundle of A1. And here I have a canonical symplectic form. And every time I can speak about symplectic forms on smooth algebraic varieties, the same way I do it for smooth manifolds. The problem starts when X is non-smooth. Such as this moduli space. So the way we're going to deal with these non-smooth cases, well, we can discuss why to do this, but we can just do it, is to replace the sheaf of the coherent sheaf of scalar forms by the cotangent complex. So if we're willing to play the same game with the cotangent complex, if I have now a smooth, let me change here. If I have a smooth, if I have a singular algebraic variety, well, I will change this definition by changing this definition. And I will define two forms to be the complex of derived global sections of the 2h power of the cotangent complex. These always make sense. The Ram differential is a bit more complicated because this is a complex. So the wedge power 2 is a complex. So when I say that the Ram differential is 0, this really doesn't make sense. So I have to ask for an homotopy in the second complex for this to make sense. And then this still makes sense. It is a form. Everything here induces me a pairing, this time living in the derived category with quasi-coherent homology. Okay, so this is a map in the derived category quasi-coherent homology, and it still makes sense to ask for this. Of course, the moment I start playing this game, I can also authorize, since this is now a complex, I can authorize forms to live in different homological degrees of this complex. In particular, I can allow my form to live in any degree n. And this time I'm going to have a shift here by n. And this time I'm going to have here a shift by n. So from the moment I accept that this is a complex, I can start playing with shifted forms. And the theory still makes sense. So the claim is that there is a shifted, a -1 shifted symplectic form on this complex, meaning an element here. So I will tell you why this is the case. But before that, I want to give you an example of such a form. Wait. Sorry? What is Tx? Tx, so in this case, I have to assume that my scheme is finite presentation. So the dual of the cotangent complex exists. It's called, so it's a perfect complex, so the dual exists. Okay? So let me give you the simplest example of a -1 shifted symplectic form. So the simplest example let me look at, let me call U the affine line. I'm writing U just to motivate what I'm going to do after. And I'm looking at the function x cubed. Okay, this is just a function on the affine line. And I want to study the critical points of this function. So I'm going to look at the points where the derivative of this function vanishes. So here I put the 0 section. And I'm going to look at this intersection. So, of course, this is just A2. And the map here sends x to the derivative of x cubed. And here it sends x to x0. So what I get as an intersection is just the spec of kx divided by 3x squared. Of course. And this is actually a derived intersection. Okay? But it doesn't matter. Let's call it S. This is a scheme. And I claim that this scheme carries a -1 shifted symplectic form. So I'll tell you what it is. So to define the form, I have to tell you what the form is. I have to tell you what is the tangent complex of this guy. I'm not going to do the computation, but I'll tell you what it is. So I claim that every time I have a thing like this, I could replace A1 by any smooth scheme. The tangent complex has a very specific shape, given by, I have the tangent complex of A1, the ambient space. And I have the cotangent complex of A1, the same ambient space where the function is defined. And the internal differential of this complex is just the Hessian of the function. This sits in degree 0. This sits in degree 1. Okay? It's a computation. It's an easy exercise you can do with cotangent complexes. In this case, you know that the tangent complex of an intersection, of a derived intersection, is the derived intersection of the tangent complexes. This is the answer you get. So let's see what happens here. I claim that there is a -1 shifted form. So -1 shifted form should produce me, should get an isomorphism or quasi-isomorphism between the tangent and the cotangent shifted. So let's see why this is true here. So if I dualize this complex, let's dualize it. So in degree 0, when I dualize, I get something that stays in degree 0. So the dual of the tangent is the cotangent. When I dualize something in degree 1, it shows up in degree -1 as the dual. And when I dualize the Hessian, I get the dual of the Hessian, but the Hessian is symmetric. So you see now why, so this is the cotangent complex, is the dual of the tangent. And now you see that actually if I shift this by -1, I get exactly the same complex I started with. So this is the simplest example of a -1 shifted symplectic structure. And there is a theorem by Brav, Bussi, and Joyce that says that locally, at Zariski locally on the scheme or Etal locally on the stack, all -1 shifted symplectic forms are this one. So locally means Zariski for schemes, Etal for stacks. Locally, all -1 shifted symplectic schemes are, so this was an example. This first thing here I wrote U and F, and this thing is actually the derived critical locus of U and F. So the claim is that locally all -1 shifted symplectic schemes are derived critical locuses. for some function u, for some function f, on some ambient scheme u. Of course, the scheme can change, the function can change, but locally they are all of this form. So, so why do we care about this? Well, because what we really want to study is the moduli space of coherent sheaves. And because of what I just told you, this guy is minus one shifted symplectic. There's a theorem. I will not tell you why. Let's just assume it. And because of this local form, this is locally some derived critical locus or some function on some scheme. So the whole point of the story I want to tell you about is the following. If this guy locally is given by a function and a scheme, I can try to glue local information about the singularities of f, the different f's I have patching my moduli space, into a global invariant of this moduli space. So the goal is to glue local invariants of singularities along this big moduli space. Okay? So let me give you 3 examples of invariants we might. Yes.
So this MCO is a stack.
It's a stack. There is a subtlety there. So it's not exactly critical locus as I wrote, but it's. There's a version of the theorem, yeah. So for the rest of the talk, I will assume that actually my M is a scheme. I impose enough conditions to have just a scheme. And for schemes, this is true. Oh, wait. Okay, so let me tell you about 3 different invariants that we might want to glue and why. So the first so let me repeat here so I just told you that locally we have these things. So let me give you 3 examples of invariants that we can extract from a smooth scheme with a function. So the first invariant would just be a number, would be the Milnor number. The Euler characteristic of the vanishing cycles for the function. So what we could try to do is to patch a moduli space with charts like this, define on every chart a function that assigns the number, so it's a locally constant function. It would assign the Milnor number for that function, and try to see that these numbers patch together over the whole moduli space. A second invariant I can try to glue, instead of extracting just the Euler characteristic of the vanishing cycles, I can try to glue the whole sheaf of vanishing cycles. So this is the perverse sheaf which leaves, actually it's a sheaf, it's a perverse sheaf on U, but it's supported on a critical locus of F. So by Kashiwara's theorem, this is the same thing as the perverse sheaf on the critical locus, which means that it actually does not depend on the ambient space. It only depends on the underlying critical locus. And the way to pass from one to the other is, of course, by taking the Euler characteristic. Another invariant that we might want to glue, it's this categories of matrix factorizations. or categories of singularities. So I will not give you the definition and the construction. I'll give you some examples in a second of matrix factorization categories. But the idea is that if f is a smooth function, this category vanishes. Otherwise, the category is non-empty. Okay? And this gives you an invariant of the singularity, which actually contains back the perverse sheaf, and therefore the Miller number, by extracting HP. So this is the theorem of Efimov. So the goal we have, the reason for this whole project was to try to glue these locally defined categories. So let me tell you two theorems. Yes? Periodic cyclic homology. Okay. So let me give you two theorems. The first is by Behrend, and tells us that these locally defined numbers glue to a globally defined function. Actually, Behrend's theorem says more than this. This is just like a remark. The amazing thing about Behrend's theorem is that if we compute the Euler characteristic of the moduli space weighted by this function, you actually get the volume, meaning the integral of the virtual class. So these are what are called Donaldson-Thomas numbers. Okay? So you can use this function to compute the volume of this moduli space. But for the purpose of the talk, this is not so relevant. The relevant is that this thing glues and why it glues. So there is another theorem by Brav, Bussi, Dupont, Joyce, and Szendroi that tells us that this local invariant, the perverse sheaf of vanishing cycles, also glues. Under a certain assumption or a certain data, a certain type of orientation is required to make sure that these things actually can be patched together. And this orientation data in the case of Joyce, what it really is the assumption that there exists a square root for the canonical bundle. So X is my moduli space. Every time I write X, it's going to be the moduli space. So if you assume that the canonical bundle has a square root, then you can patch these things together in a global perverse sheaf of the moduli space. X is the moduli space.
Doesn't Joyce have a theorem that says that ky has a square root, and so does kx? Joyce, not mine.
If what, sorry?
If y itself
has a square root.
y has a square root.
But the canonical bundle of y is trivial.
Yeah, so it has a square root.
But no, it's not enough. Sorry, the theorem of Joyce
Yeah, I thought Joyce had upheld
for
something.
you're saying that it always exists such a guy in the Calabi threefold.
Yeah.
Yes, but I don't need it here.
Yeah, okay.
Yes, it's true. I'm just telling you that there is something necessary to patch these moduli spaces. I'm not discussing the existence of this necessary thing. Okay? I don't understand their theorem. Okay. So let me state our theorem. So X, in this case, is a -1 shifted symplectic scheme. Okay, we don't have the results yet for stacks. Still, you have the Darboux, you have this local form. So the claim is that these locally defined categories on X, glue on X, as a sheaf of non-commutative motifs. So we don't claim that the categories themselves glue, but when you pass to non-commutative motifs or even to motifs, the motifs of these categories glue under the prescription of 3 orientations. So in that case of Joyce, there were one single orientation data that was required. In this case, there are 3 classes that you have to trivialize in order to glue this. So the first class lives in a tal homology of X which values Z mod 2. The second class lives in the second group. And the third class lives in the third group. And this is all you need to trivialize. So I will explain you in a second why these 3 classes appear. I will try to convince you that this class is the one that already appeared in Joyce's work. And why and how we come to these 3 classes and only these 3 classes and not an infinity number of classes. So in order to explain you the nature of these classes, let me give you some simple examples. So let me make this picture for you. So let's please go to the simplest possible -1 shifted symplectic scheme. A point.
Excuse me, Z2,
Yes.
Z mod 2?
Is Z mod 2, yes. So, yes, is Z mod 2 every. Actually, this is not 3, this is 2, and this is actually mu. This is actually mu 2. Sorry, this is Z.
That is accurate, no?
Yeah,
So it's not Z mod 3, it was just a typo.
it was just a typo. It was just a typo. Sorry. Yes. So let me tell you the simplest example and why you already see 2 orientations showing up. Okay. So if X is a point, the simplest example. If I want to write the point as a derived critical locus of a function, I can write the point with the function 0. Okay? Not much going on here. So if I look at the perverse sheaf, what I get is the constant sheaf C. Not much. But here I already start having something interesting. The category of matrix factorizations that I get on this guy is actually the category of 2 periodic complexes. So that's by definition what is a matrix factorization. So I didn't tell you what it was, but just think about complexes with an action of an operator of degree 2, which is invertible. And another example of a local function that gives me the same critical locus would be A1 with the function x squared. In this case, the perverse sheaf I would find, is actually of dimension 1. It's of dimension 1, but it's so it's a priori isomorphic to this, but non-canonically. And the reason is that essentially I have to choose an orientation here to match this to C. So there are two possible choices I can have here. And the two possible choices are related to this class, beta. So, and things get, so this is isomorphic but non-canonically, so there is an ambiguity going on here. And the situation is even worse here, because what I get is one periodic complexes. I'm over C. Everything is over C.
But H1 et al. on spec C is 0.
H1 et al. on spec C. Oh, yes, in this case, it's trivializable, the class. Ah, you mean, yeah. Yeah. Okay. Everything is 0.
But then what's the orientation choice?
Well, here you have to choose an orientation for the S0 that lives here. The 2 points. Well, if you, it's instead of dimension 1. And there are 2 possible isomorphisms you can put here. So
Oh, I see. You could say x to x or x to
minus x. Yes.
X squared invariant.
Yeah. Okay. Thanks for. So this case is actually different. And this difference is the origin of this class. So this class here will correct essentially the parity of the dimension. And you're going to see now that why this shows up. I can also do this. Again, these two things are isomorphic, but non-canonically. And here what I get is actually an equivalence with the first complex. So this is known as Knuller periodicity. But this requires a choice. And the choice is the choice of a Lagrangian inside this guy. So this is a quadratic form of a maximal isotropic. And actually, in this case, for this equivalence, there are only 2 things that matter. There are only 2 possible choices, because the equivalences, auto-equivalences of this category are only 2 possible things, either the identity or a shift by 1. So there are only 2 possible automorphisms of this category. And this corresponds to the 2 possible choices I can have for this choice of isotropic structures. Either I put a Lagrangian, one isotropic structure, or the complementary one.
So isotropic for what?
For the quadratic form.
But what if you're over R?
I'm over C.
Yeah, I know you're over C.
If you're over R, there are more choices. Yeah, it's complicated.
Okay, great.
Yeah. So, and the class gamma, it's not clear for us yet what it is. So, but you already see that if you want to glue these things, there are plenty of ambiguities going on. First, you have to be sure that you match the parity of the dimensions. Otherwise, these 2 things do not agree. Then you have to be sure that you match, that you are compatible in gluing with identities or minus identities. So there's a sign going on here. This is what this class is for. And so let me.
Marco?
Yes.
So these 2 periodic complexes are secretly modules of the S1 tape construction.
Yes.
And is there a similar interpretation of a 1 periodic complex?
I don't know.
So it's just literally, I mean, it's just defined naively.
Naively, yes. I don't have any interpretation for that. Okay, so let me tell you about what we actually do. The idea of the proof of this theorem. So the first thing we will try to write down is, so all our constructions, what we're trying to glue is local information about the symplectic form. So what we will try to do is to define a moduli space first that kind of explains how these local models vary. So I'm going to give you a definition. So I'm going to, in my case, X is a scheme. So I'm going to define for you a construction, an étal stack, an étal sheaf over the small étal site of X to spaces or infinity groupoids that does the following thing. On every étal over X, I will look, I could take, for instance, open immersions, but I think this is the easiest way to do. So for every open neighborhood of a point on X, I will look at the collection of all possible identifications of my, so this is symplectic, this is étal, I can pull back a symplectic form. So I can look at all possible identifications of S with the derived critical losses. Some U and some F prescribed. So the first thing is that if you just define this like this, so the data here is a symplectomorphism, a U and an F. This is not even functorial if U is just is a scheme. Because if I have a map étal over S, I don't know what to pull back. No, X is given a symplectic form, and S is given the symplectic form given by pullback. So on every étal neighborhood, I pull back I restrict my form. I'm giving the symplectic structure on X. Okay? So what we're going to do to make this a functor is to assume that X is a formal scheme, smooth. And we assume also, so there is always an embedding of the critical points inside the ambient space. We will assume that this embedding is an ISO on reduced subschemes. So in a way, it's just the nil thickening of S. And if I had something which was algebraic, I would just take the formal completion along the critical points and replace my original U by the formal completion. And the restriction of F is just a Taylor series. Okay? So the moment I replace algebraic by formal, this thing becomes a sheaf, becomes a pre-sheaf, and claim this construction defines a sheaf on the small étal site. Let's give it a name. I will call it Darboud of X, because these are Darboud local models. So claim Darboud X is an étal sheaf on X. So this gives me a moduli space for local parameterizations of my scheme as the derived critical locus. So why do I care about this sheaf? Well, because all the invariants I was trying to define before are actually defined naturally on this sheaf. So the first invariant I told you about was the Milnor number. So on the étal site, you can look at the locally constant sheaf with value Z, and you have a canonical map of a natural transformation of pre-sheaves, of sheaves, that on every S sends a local model on F to the Milnor number on F. Another thing you have is that perverse sheaves form a stack for the étal topology. So you can look at the stack of perverse sheaves. And the map sending a locally defined function defines a natural transformation from, if you have S étal over X, you send UF to the perverse sheaf UF. So this is a map of sheaves. This is a map of sheaves. And another map of sheaves is the map that sends, so there is another stack on the tau side, which is a stack of DG categories, of sheaves of DG categories. So if you have a local model, UF, you can locally define MF as a natural transformation of sheaves. So the moment you have these, the gluing problem becomes a simple, you can reformulate the gluing problem as a descent question. So I erased Barron's theorem and Joyce's theorem. But what they actually say, so Barron, in this language, what Barron's theorem says is that you have this map of stacks. And the gluing is the fact that this map factors through the final sheaf. If you have a map from the final sheaf to the constant sheaf, it's just a global section of this sheaf, so it's a function. So Barron's theorem says this, and Joyce's theorem again says that there exists a factorization through the final sheaf. So it's the existence of a globally defined perverse sheaf. So if you want to glue locally defined invariants with values in any stack, what you have to show somehow is that it factors through the point. So let me tell you our actual theorem. So we would like to say that this Darboux stack is very close to the point. So there are two things that make this Darboux stack actually very close to the point. The first thing, which I kind of made implicit in some 20 minutes ago, is that if you have, I started with a point with a zero function, I added a quadratic function, and I added another quadratic function, yes?
So in this theorem is this factorization the same thing as an orientation?
You will see in a second. So I told you that I could add quadratic bundles, and it would not change the critical locus. I did it in a point. I did a1 x squared, then I did a2 x squared x y squared, and the critical locus is always the point. So there is some action of the stack of quadratic bundles on my Darboux charts. I have to be a bit precise here. I have to tell you about what kind of quadratic bundles I have here. I actually have some kind of quadratic bundles with a flat connection. I need this flat connection here, but it doesn't matter much for the purposes because locally they are all trivial for this case. So I have an action of the stack of quadratic bundles, which is if I have u, which is a function, and I have a quadratic bundle, I can always do times q, f plus q, and the derived critical locus is just a derived critical locus of uf. So it doesn't change the critical locus. So let me draw this diagram again. So I have this structure sheaf. I have this locally defined perverse sheaf, sorry. And I just told you that I have an action of quadratic bundles here. And actually, there is an action that this action becomes something else here by taking the determinant. If I take the determinant of a quadratic bundle, I get something whose square is OX. So here, I land inside the copy of BZ2, which is exactly the stack classifying square roots of the structure sheaf. It's the fiber of GM to GM. And this acts here. So this is Joyce construction. I'll not describe you what this action is. But the key point is that there is an invariance of this functor. And actually, I could do the same here. I could do the same for matrix factorizations, replacing these by digi categories and these by Azumaya algebras. I'll not have time to explain this. But the thing is that this whole action is compatible, and this compatibility is called the Thom-Sebastiani theorem. So in particular, this passes to the quotient. So you already see that if this was the point, as I claimed, as I was trying to give you the idea here, you would have automatically defined a twisted perverse sheaf up to a BZ2 action. And the question of orientation is, when can I leave this there? And this is an easy question, because you know that if you have an action, you can recover the space where the group acts by taking the fiber product over the classifying space of the group. So you already see that if this was the point, this map would classify me a class here. And to trivialize this class, this composition, is to say that it factors for the trivial bundle is to give a lifting is to give exactly a perverse sheaf. So let me tell you, to finish the talk, let me tell you what is our theorem, our actual theorem. So we would like to say that if you mod out by the action of quadratic bundles, you get something contractible. But this is not true. And the reason it is not true, so you see, for this to be true, you would need that. So first, you would need the action to be transitive. This is true. But you would need every automorphism of a given critical chart to come from an element in ON. And this is not true. So an example, let me fix a critical chart given by A2 with the function x cubed plus y to the fourth. And let me give you an automorphism that does the following thing. Sends x, so it's going to be a formal thing. It sends x to x plus y to the fourth, and sends y to hy, where h is whatever you will get when you try to make this automorphism that preserves the function. So actually, there is a condition, is h4 equals 1 minus a bunch of stuff. So if you fix the h correctly, then you get an automorphism. And this is not the same as something that would just come from would be the identity in this case. Okay, it's not coming from an element in ON. But you can do a bit of magic here and multiply by t. So you can build a one-parameter family of automorphisms that interpolate between this guy and the identity. So what actually is going on here is that if I take this stack and I kill these isotopies, this kind of automorphisms of foliation of critical charts that are A1 homotopic to the identity, what I get is this. And this is our theorem. Okay? So maybe to finish, let me just write where these orientation classes come from, the 3 of them. So
Before you get into the example, what was you're changing x goes to x plus y to the 4th.
yes, and then y goes to h times y, where h is a function that depends on x. So it is.
So what was the original function? The original one?
So this is the function, and this is the automorphism.
Oh, that's an automorphism of that.
Yeah. So the problem is with the automorphisms.
Oh, okay.
Okay. So let me give you. So first of all, you can already see here. Let me also actually write it here. You see, the theorem doesn't say that this is the point. There is a map to the point. But the theorem says that if I quotient by isotopies, then this is the point. So there is still the question why these factors through isotopies. So in the case of perverse sheaves, this is because perverse sheaves have a one invariant for morphisms. There is rigidity for perverse sheaves in the sense that perverse sheaves on X and perverse sheaves on X times A1, it's fully faithful. So if you have a one parameter family of automorphisms on the perverse sheaf, this will not see the T. It will be constant. And this is why these factors. And this is how we recover Joyce's result from this statement. So, and let me, to finish, I think I have 1 minute left, 2 minutes left. Let me maybe tell you what's going on for matrix factorizations. And there was a whole other story we can actually, I could tell you about, is the fact that I chose to describe the picture for you of what happens with -1 shifted forms. There is a notion of -n shifted forms. And what you're going to see here, instead of quadratic bundles, you're going to have shifted quadratic bundles. And there's a whole story with the Grothendieck-Witt groups going on behind the scenes, which I will not have time to explain, but if you have questions, I can try to. So let me just finish with the description of what's going on for MF. So far, the problem so far about MF is that we don't know if the category has this sort of rigidity for morphisms. We don't know this. This is why we cannot, for the moment, glue the category of matrix factorizations. But this is a problem that we solve by gluing the non-commutative motive associated to MF. Okay? Because there you have A1 invariance and you kill all these isotopic families. And so let me describe to you where the orientations come from. So you have this Radboud stack. And now you want to go to stacks of DG categories, which are 2 periodic over X. So locally, you're sending a pair UF to MF. So now, I told you about this action of quadratic bundles. And on this side now, every time you have a quadratic bundle, you have this Thom-Sebastiani theorem that tells you that this square is the unit. So this becomes a 2-torsion element in invertible 2 periodic categories. So this becomes, let me write it this way. So MF of a quadratic bundle is always Azumaya. These categories are 2 periodic, so these are 2 periodic Azumaya. But there is this extra 2 torsion. It's the clue I should finish. So what is really going on behind the scenes now is that, well, you have to descend these to motives. Let's say we descend these to non-commutative motives. But what is really going on behind the scenes now is that the orientation that you're going to get is going to be, before it was classified by B of the group that acted, and here is classified by, again, B of the group that acted, that acts, to periodic, to torsion. So you have to compute the Motivic groups of this stack, and you're going to see that because of the two torsion, everything stops in degree 3. You only have pi 1, pi 2, and pi 3, which are exactly the classes I described to you in the beginning. And this is why, well, that's the origin of these three classes. So it has pi 1 given by these two elements These are the two possibilities. The pi 2 comes from the automorphisms of this category, which are only the identity or the sheaf by 1. And the pi 3, well, it's again a Z mod 2, because it's the kernel of a multiplication by 2 map in the Azumaya points. And then pi n are 0. Exactly. You just do obstruction theory, exactly as we did there. The only obstruction was in the H2. Here, the obstruction lives in 3 classes. And that's why the orientation is much more complicated than in the previous case. And I guess I'm done. Sorry for the time.
Do you have any questions for Marco?
So as far as I understand you, one reason to work over the complex numbers is to make the orientation business work out, but are there other things in the story that will break down if you were to apply this over another field?
I think there are way deeper obstructions than that. The fact that I don't know how to define a shifted symplectic form away from the I mean, I could define it over Q, but I never tried to see what this gives over Q. But so there is, first, to work with other fields. First, you have to define what is a shifted symplectic form structure. Then you will have to prove this Darboux lemma, this local form, which I don't know if it's true. So I don't have any field. The reason why we work in this context is because the only one we know how to do. I don't have a more philosophical. Yeah, I don't know if this answers your question. Sorry. Yes.
So, do you have an interpretation of the pi 3 since it's mod 2 no interpretation?
It's just like
Compute it and
I compute it, but I don't know what it is.
yeah.
I don't know what the class represents, right? So.
And what is this as 2p 2 torsion? Did you say what is that again?
Two torsion is just the fact that
What's this as thing?
Azumaya.
Yeah, Azumaya, but what does it represent? What is it?
So it's just the stack. I mean, I don't know what.
I don't know what it is. What's it stack representing?
It's invertible DG categories.
Oh, invertible DG category.
Yes, in the Morita theory of DG categories.
Oh, with respect to tensor.
The tensor, yeah,
Oh, okay.
yeah.
Why
Because
what does that have to do with Azumaya?
because these are right. Azumaya you can see as in the Morita theory is just A tensor A op is the trivial guy, right?
Oh, okay.
So
So
that-
that's just saying it's invertible.
And it says invertible.
Oh,
Yeah.
okay.
Sorry, it's a fancy language to say something simple.
Azumaya algebra. It's just that it's invertible.
It's invertible. Yeah. Yeah.
Great.
Well, if it was compactly generated, if it modules over an algebra, you would get back this notion, right? Because you are in the Morita theory.
Oh, okay. Cool.
So that's the.
I see. Special. That's great.
So you are hinting at something with unshifted structure.
You were sure you want to start me on that? So the thing is that if you have a shifted symplectic structure, you can actually build a quadratic form by shifting your complex by 1. Right? If you have something which is -1 shifted, a complex which is -1 shifted symplectic, you can always shift the complex by 1, and you get something which, so there is always this game where you have a symplectic complex or a quadratic complex by shifting by, and this shifts by 2. You get something which is 2 quadratic, right? So let's say you have a map classifying your symplectic form. Going to -1 shifted, it goes to 2 quadratic. And then you can send this to the Grothendieck-Witt of 2 quadratic. And then you can play with the sequence that tells you that the Grothendieck-Witt of 2 quadratic fits in the sequence where you have K-theory, the hyperbolic map, and quadratic -1. So you can go So there is a map to the suspension of Grothendieck width 1. If I'm not mistaken. Sorry. Plus 2 is 1, 1, 0. Very good. So you see, every time you have a scheme which is -1 symplectic, you get this map that lands in the suspension of the Grothendieck width. Something I didn't mention in this story is that every time we take the quotient, quad is a monoid, it's not a group. So there is a group completion going on. So actually what you have there is not B quad, is the Grothendieck width. So you land in the same place. This is B quad. Okay? So this map is that map. They are the same map. And now you can imagine doing the same game where you change symplectic -1 by symplectic -2, -3, -4. You always have this boundary map, and you're always classifying something. And there is analogous of this Darboux stack that works for -n, and there should be a version of the theorem for this -n, and the same story should be going on. Well, we haven't really tried to attack this problem, -n. Yes?
Could you bunch all those shifts together in a single object?
Sorry?
Could you bunch all those shifts together in a single object, like you do for like
Shifts? What shifts? Sorry.
So you have these shifted like symplectic forms or shifted quadratic.
Yeah, it's something that lives. It's a tangent bundle of X. So it lives here.
Yeah, exactly. How can you bunch them all together into like a single thing? Because you can bunch all the shifts of like Grothendieck width into a single spectrum, right?
But I don't know what this means geometrically, right? I know what is a n shifted guy. I don't know what is for all n's. What does it mean? Is this something like this you're suggesting?
Yeah.
I'm confused. But yeah, I don't know.
All right. So if there's no further questions, let's thank the speaker again.
Thank you.